And you've got a great story, haven't you, about where the name bug comes from?
Absolutely. So the very first bug was literally that. It was a moth that flew into a piece of electrical equipment in a factory and caused a short circuit, and hence a malfunction of the system. And if you search online, you can actually find an image of the engineer's notebook where he's taped the hapless creature into his notebook.
Hello and welcome to Ingenuity, the podcast series from HORIBA MIRA, where we go behind the scenes of next-generation vehicle development. In each episode, we'll take a look at a technical area of expertise and show you the mastery that lies behind the magic. I'm thrilled to be joined in this first episode by Dr. David Ward.
Thank you.
Welcome, David. Now, before we get into functional safety in your area of expertise, can you just tell us a little bit about yourself?
Yeah, so I'm David Ward. I'm Global Head of Functional Safety within our vehicle resilience activities at HORIBA MIRA. So my role is working with people at all stages of maturity, various places across the world, all the way from vehicle manufacturers right down to hardware, software, silicon level, helping them to understand and implement functional safety and doing independent reviews of what they're doing.
You're a very busy man. And many people listening will know what functional safety is, excuse me. But for those of us who don't, can you tell us what is it? What does it mean?
Yeah, so in a nutshell, functional safety is about ensuring that malfunctions in electronic systems in vehicles don't pose an unacceptable level of risk to people, whether they're people in the vehicle or indeed outside the vehicle. Those malfunctions can ultimately be traced back to faults in the hardware or to shortcomings in the way we specify, design or implement the system, the hardware or the software. And what we have to do is to ensure that where possible we design those out of the system, and if failures still occur at runtime, that we manage them in a safe and predictable way. I think we're all familiar with the blue screen of death on computers. If that happens, you have some choice words to say about your choice of technology provider, but you shrug your shoulders, you reboot and hopefully carry on as if nothing had happened. When we're dealing with electronic systems in vehicles, we're dealing with safety-related real-time systems where they have to make the right decisions often in milliseconds, so much faster than human reactions. They have to make the right decisions, and if there are any malfunctions, we can't present the driver with the blue screen of death. We can't say, please stop your vehicle and reboot it. We have to, generally speaking, carry on operating in a safe way, or if a system has to stop operating, we have to remove its functionality in a safe and predictable way.
Yeah, definitely. I think we'd be petrified, wouldn't we, if we got a blue screen of death in our vehicles. So what causes these malfunctions?
Well, as I said, ultimately they're traced back to faults in the system, the hardware or the software. Particularly for hardware, those can be faults where something breaks or wears out. So there's a physical failure, if we put it that way. But the bigger class of failures that we're often having to deal with are where there's a mistake in the way something is specified, designed, implemented, or tested, and those can be found in the design of the overall system or in its hardware or in its software. When we look at the world of software, colloquially, those are called bugs, but it's more accurate to describe them as defects or faults in the way that the software is being specified or implemented. To give you one very good example, the Post Office Horizon system is very much in the news at the moment. There was a case there where a postmaster found a deficit. They rang a helpline who told them you're permitted to make a manual adjustment to correct it, but when the sub-postmaster followed the correction steps, the deficit doubled. And what they found was that somewhere in the software, someone had put the wrong sign in an arithmetic expression. So essentially, a value was being added rather than subtracted. That's a good example of the type of defect or mistake or fault that's present in something like software that, as we've said, is colloquially called a bug.
And you've got a great story, haven't you, about where the name bug comes from?
Absolutely. So the very first bug was literally that. It was a moth that flew into a piece of electrical equipment in a factory, and in an act of self-immolation caused a short circuit and hence a malfunction of the system. And if you search online, you can actually find an image of the engineer's notebook where he's taped the hapless creature into his notebook and said, I found this bug in a particular relay panel. When we're dealing with things like mistakes in software or a bit flip in a semiconductor device caused by cosmic ray or something like that, they're very different to that, but they're no less serious in terms of their potential outcomes.
Yeah, definitely. So let's go on a bit of a journey. Let's go back in time. When did the world first get interested in functional safety?
Well, the world first got interested in functional safety really as soon as we started using electronic systems and computers in safety-related applications. But the emergence of functional safety as a discipline really started in the 1980s. There were a few key incidents that occurred. One example, and one of the best known, is something called Therac 25. This was a machine that was developed for delivering radiation therapy. Previous generations of the machine had already used computers and software for some monitoring and data recording purposes, but because that software worked so well, they decided to make it more responsible for the control of the machine, and in particular they moved some of the safety relevant interlocks from hardware into software on the assumption that software could never fail, and if it functioned correctly, then it must be right. And over a period of about 18 months, several incidents occurred where patients were delivered massive overdoses of radiation, and this became very much a seminal incident that when it was investigated, it was found, there was a lot of misplaced confidence in the abilities of software to work correctly, in its abilities to deal with incorrect or incomplete information, for example. So that was really one of the incidents that kick-started a lot of the interest in the discipline that we now know as functional safety.
Yeah, so we thought it was magic, this software, and actually it's not, is it? No, that's a really important point. And when did you first get introduced and involved in functional safety?
Well, going back to what was going on in industry as a whole, once industry started to get interested in functional safety, some standards were started, and in the late 1980s, early 1990s, there were two draft documents in circulation in one of the global standards making bodies, one concerned with general aspects of functional safety and one concerned specifically with software. And around that time, the UK government recognised the importance of this emerging discipline and ran a collaborative project. The UK government recognised the importance of this emerging discipline and ran a programme of collaborative projects called Safe IT. And they encouraged various industry groups to form consortia to research the implications of functional safety and what its application would mean to the particular industry sector. Of about 20 projects, I think there was only a handful that were successful, both in terms of delivering something and delivering meaningful and enduring output. And one of those was a project called MIRA. This project came out of a former software reliability working group in the SMMT, the Society of Motor Manufacturers and Traders, and it was decided to have a collaborative project amongst a number of organisations to write some guidelines for software development in vehicles. So although the book that we published is called Development Guidelines for Vehicle-Based Software, it's really about functional safety. And this was published some 10 years before work started at the international level on ISO 26262. This was the beginning of my involvement in functional safety, so I was first of all asked to support some of the technical tasks that were being used to develop content, and then I took on responsibility for project management and the overall running of the consortium. And as I say, we published this document nearly 30 years ago now, and I think one thing that was significant was at the time this was shown to a representative of one of the government departments who saw the logos on it and said, well, if those companies can agree about something, then it has to be worth paying attention to.
Yeah, definitely. I think this is the really interesting part of the story for me, this collaboration and consortium of industry that's come together for the good of functional safety.
Yeah.
And so tell us about ISO 26262 then, and standards in general. Why are standards important, and why particularly that one?
Yeah, so standards are important because they provide us a framework for engineering activities, and in particular way to have a common approach, a common language in the supply chain. So if we look at the automotive industry, there's a complex multi-tiered supply chain, and typically development of a vehicle and development of the systems in a vehicle will start with the vehicle manufacturer saying we want one of these, but there's a lot of input from technology providers. So we need a way to communicate requirements and activities within the supply chain and to have a common approach. So standards are really important in that respect in terms of having agreement on what's the industry approach, to have something to hold up to say this is the way the automotive industry does functional safety, for example. So even though we had things like those MIRA guidelines, even though we had individual companies pursuing their own internal safety standards, it was recognised that we needed something to hold up to say this is the automotive industry standard, this is the common globally agreed approach to functional safety.
And so tell us a bit about the role of MIRA as it was then in this. We were very much bringing the industry together, weren't we?
That's right. So we very much helped bring the industry together in development of those original guidelines. And then when work started on 26262, I got involved representing the UK industry position in the international committee that develops the standard. And that's a role that I've continued to hold ever since.
So tell us, David, who does functional safety apply to, and where does it apply?
So I would say, very simply, functional safety applies to anyone that's developing a safety-rated electrical or electronic system in a vehicle. And the premise of 26262 is that we should assume that any electronic system in a vehicle is safety-related until we've demonstrated otherwise. Usually, if a system genuinely is not safety-related, we will find that out fairly quickly through activities such as the hazard analysis and risk assessment, for example. But I think when we first started on the journey of functional safety, it was fairly clear-cut what was and wasn't in scope of functional safety. Now, because electronic systems in vehicles are so integrated, are so interdependent, it's actually becoming much harder to find something that 26262 does not apply to. And 26262 applies to anyone that's involved in the supply chain of developing an electrical electronic system. The way that the standard applies will vary depending on the context. So the activities that a vehicle manufacturer will do, for example, are quite different from a supplier that's designing the electronic circuits or developing the software, for example.
And it's not a recipe book, is it? A standard?
That's right. That's a really important point. So if we look at go back to the question of why standards exist, if we go to ISO, which is the International Organization for Standardization, if you look at their definition of a standard, they say that it represents the collective wisdom of experts. It represents an agreed industry approach, and we can very much say that for 26262. But also, interestingly, they say to think about a standard as a recipe or a standard way of doing things. And certainly there are a lot of standards that are written like that. They're a standard method of taking a measurement or performing an activity so that if you follow the standard, it's done repeatably and consistently between different organisations. So, for example, there's a British standard about making a cup of tea.
Of course there is.
Well, why is there a British standard for making a cup of tea? It's actually related to temperature measurement and having a standardised reference that you can use to determine the performance of temperature measuring devices, for example. So clearly a standard like that is very formulaic and one where you can walk through and tick, 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 yes, we've done the steps. The problem is that 26262 isn't that kind of standard. It's an engineering framework. It's a process, effectively, that tells us the steps that we need to follow in order to develop a safe system and to achieve functional safety in that system. I think, unfortunately, because of the perception that some standards, at least, are very formulaic, some people have tended to approach 26262 with that tick box mentality, saying that it's just something that we seek compliance with as an end into itself. But it's really important to understand it as a process framework and a tool tool to help us develop safe systems. We don't comply with 26262 as an end in itself, but we follow it because it helps us have a common approach and follow the agreed industry understanding about the best way to develop safety-related systems in vehicles.
And that's where organisations like HORIBA MIRA are so important, aren't they?
That's right, because we bring a wealth of knowledge and practical experience in terms of applying these standards. We have the insight of having helped develop the standards. So, as I often like to tell people on training courses, we're approaching this from the perspective of knowing not just what the standard says, but what it means, because with these things being developed by committees, sometimes there are nuances in the language and in the backstory, if you like, that it's important to understand. And the reason we do that is, not to have some secret knowledge that's only for a select few initiates, but rather to help people understand the thinking behind the standard and the way that it's intended to be used, so that ultimately we achieve the objectives of developing a safe system.
And can you tell us something about functional safety that people might not know?
Yes, an interesting fact is here at HORIBA MIRA we have a vision that every journey will be positively influenced by it. And in fact, our activities in functional safety have arguably achieved that already. We talked about the work of the MIRA consortium and how, as part of a funded project, it developed those functional safety guidelines. But actually, when the funded project finished, some of the members decided to continue working together because we recognised that we were on to a good thing. So even though it continued as an informal, unfunded activity, it went on to develop things like MIRA-C, for example. MIRA-C came about because two of the consortium members discovered that they were each writing guidelines for their suppliers on how to use the C language in developing software for automotive systems, and said, wouldn't it be a good idea if we collaborated and had a MIRA publication rather than continuing to do our own thing? So we brought together another group of people to write MIRA-C, and although that was originally released for automotive use, it very quickly got noticed in other sectors and by tool vendors, and it's been effectively adopted as the de facto standard across a wide range of industries, including pretty much all the transport modes, and even some of the Mars landers have software in them that's been influenced by MIRA. So actually I'd argue that, the work we've done in functional safety hasn't just influenced every journey in the world, it's already influencing journeys off-world as well.
I was going to say it's gone intergalactic.
That's right, yes.
That's incredible. What an incredible story. Thank you very much for your time today, David. I think this is such an uplifting example of the importance of industry coming together and organisations like HORIBA MIRA being the independent enabler for that as well. So I know we're going to touch on the present and the future for functional safety in the next episodes, but thank you very much for joining us today.
Thank you.